Okay, so thank you very much. Thank you for the invitation. It's a real pleasure to present this work, which, as I was saying earlier, to those who were here, might not be the most recent, but is still quite interesting to reflect on what machine learning can tell us about phase transition. And this was sparkled by the curiosity I had in the sense that phase transitions are about patterns. For instance, if we take the IC model and we look at pictures, if the two phases are deeply in the symmetry broken or in the symmetric phase, we are able to tell from the image. And this is what machine learning is actually pretty good at doing. So taking images and tell what are the characteristics of those images and reconstruct the patterns that make them. But the question that I ask is whether we can go a little bit beyond that qualitative feature and how much we can push machine learning from the quantitative point of view. This is work that I've done in collaboration with Hertars and Dimitrios Baktis, especially Dimitrios, who was our PhD student and has been the real driving force beyond this project. So this is an overview of what I'm going to talk about. I'll start by arguing that machine learning could be a useful tool to augment our physical intuition. Then I will go back to our traditional physics background. I will introduce methods and models. I will move from there to a quantitative characterization of phase transitions using machine learning. I will see that actually machine learning is not just able to reproduce what we know, but also to give new information. And finally, I will conclude with an overview of how machine learning can be used to provide an inversion of the renormalization group. I will summarize and we'll see where we can move from here. So, as most of you know, and I can tell those who don't, I'm a lattice field theorist. And what I like about lattice field theory is that it is a first principle method for calculations in strongly interacting quantum field theory. And it's especially useful when the coupling constant is of the order 1. With the lattice field theory, we discretize the model on a grid, and then we perform calculations with Monte Carlo methods and extrapolate the result to the zero lattice spacing so that we can reconstruct the physics of the continuum. So this calculation is well controlled. So from the point of view of the theory, we have all the ingredients in the right place. Whether we are able to do that in practice or not, that's another matter. And that's where most of the energy is going. But in addition, we have the problem, the issue that there is a lot of computational time that is needed in order to perform a well-controlled lattice calculation in QCD. And in fact, it's estimated that about 20% of the supercomputing power in the world goes into lattice QCD. So at the moment, machine learning is one of the tools that the lattice is looking at to see whether it is possible to increase the efficiency of the calculation, for instance, by using machine learning to generate configurations, still exactly, or improving the algorithmic efficiently, or to find new ways of analyzing observables or even improved observables. Machine learning, the lattice is not the only field that is looking at machine learning. What machine learning is as a field of artificial intelligence, and it's a collection of various methods. We live in the era of deep learning, which has been enabled again by our ability to compute. But other methods of machine learning are much older than that and go back to the 60s. For instance, the support vector machine has been around for about 40 years. Another enabler of machine learning is a number of very optimized and ready-to-use libraries, for instance, TensorFlow, Scikit-learn, and PyTorch, that are sponsored by big companies such as Google and Facebook. By now, machine learning is used in various fields of physics, and in any conference you are going, probably there will be at least the odd talk of machine learning, or maybe even a section dedicated to machine learning. There have been several machine learning studies, and more as we go on, following a seminal work of Melko and Karaskila that I'm going to briefly review shortly. Machine learning has really been exploding in the field of high-energy theory. This is a plot, if you look on Inspire, for the work that has in the title Learning, and you will see that until 2022 we have had an exponential law with some sign of saturation. It looks like this is now saturating, and it could be just another demonstration of the Amara's law, which essentially states that at the beginning we tend to overestimate the effect of a new technology until there is a compensating effect, which then leads us to its underestimation in the longer run, and asymptotically its use will settle somewhere in the middle. So we may be just reverting from the overestimate of the usefulness to the underestimation. So it's possible that this curve will go down to then settle somewhere in the middle. Before moving to what we are doing with machine learning, let me start by quickly reviewing some models. And I could not have started from the IC model, which is the model that we all know and love due to its simplicity and at the same time insightfulness. This is a popular test bed for numerical approaches, as we can solve it exactly at external field equals 0. The variables are spin variables that are distributed on a grid of size L. I'm using predominantly 2 dimensions, and this is where we actually can solve the model and where the physics is interesting. The Hamiltonian is written here. It has a nearest neighbor spin coupling, and which at h equals 0 is spontaneously broken as a Z2 symmetry that is spontaneously broken. We can write the partition function, and we can solve for the critical temperature from the broken symmetry phase to symmetry restoring phase, which has the value that you can read down there. The phase transition, again, has a natural order parameter, which is the magnetization, which is the average of the sum over the spin variables over the grid. So if I take the limit L going to infinity, the magnetization is different from 0 when the temperature is less than the critical temperature, when it is equal to 0 in the symmetric phase, when the temperature is bigger than the critical temperature. I'm trying here to up the game with respect to the early study. So what I'm looking at is trying to reproduce the critical exponents, and in particular the critical exponent of the susceptibility, which next to the critical temperature in the critical region scale as the difference of the temperature with the critical temperature to the exponent of minus gamma. Likewise, the shift at finite volume in the critical temperature scales like the sides to the -1 over nu, where nu is the critical exponent associated to the correlation length. And since... Sorry, is there a question or no? Okay. Since I'm restricted, of course, in numerical simulations to the final lattice size, I will be extracting critical exponents from the shift in the critical temperature and from the scaling of the maximum of the susceptibility, which goes like L to the gamma over nu. Once I have these two critical exponents, using the scaling law, I can reconstruct the four phenomenological critical exponents that characterize the model. A generalization of the IC model is the Potts model. I'm still staying in D equal 2, and I'm using this Hamiltonian, which again has a nearest neighbor coupling with the delta function. So this contributes 1 if the two spin variables are the same, or 0 otherwise. The spin variable gets value in the number of states, which is an integer. And here you see a picture for the number of states equal to, which is the IC model, 4, 6, and 10. This picture will be another seminar, actually, because it's very complicated to obtain with traditional methods, especially at large Q, due to these big metastabilities that you will see with this jump, for instance, at Q equal 10. So this has been obtained using a density of state method. And the last theory is a simple field theory that I'm going to use, which is the self-interacting scalar field in dimension 2. Again, kinetic term, nearest neighbor coupling, plus the lambda 5 to the 4 potential that we all know. For our simulation, we fix the kinetic term equal to 1, and we find the constant of the kinetic term equal to 1, and we find the critical line of points, which depends on the ratio of the lambda over mu. We will use as a reference a work by Sheikh and Loinas, which finds these two values, and these will be the two values that we will try to reproduce. And now let's go down to machine learning. And what I'm doing here, what I will be using is mostly what is called classical machine learning or statistical learning. Statistical learning is devised in supervised when you input information on the system and you are trying to characterize using that information unseen data sets, and unsupervised where you are looking for regularities. I will be working on the far left here, supervised and classification. Classification is when you have a label and you are finding patterns which will distinguish the values of that label. Now, what are the questions that we will be asking? So the first question is a rather natural one. Can we use machine learning to detect a phase transition? And then among the various algorithms of machine learning, are there some that are better than others? And how would you characterize being better? Increasing the sophistication, I can ask whether machine learning can find an ordered parameter, whether it can reconstruct the symmetry that drives the transition, and whether it can determine with the statistical accuracy that is comparable with other methods, the transition temperature and the critical exponents. And finally, what really motivated in my mind all this study is if we can see features such as topological excitations that are relevant for the phase transition. I will conclude then with the inversion of the renormalization group, which I will define in due time. Again, the characterization of the topological excitation will be another seminar that I will not give today. Most of the work that we have done use convolutional neural network, which is one of the most used methods in machine learning. It's a deep learning method, where deep means that you go through several layers of those processors or filters. And it's particularly appealing to physicists because convolutional neural network respects translational symmetry. So we don't have to worry about breaking translational symmetry. This is an example. These yellow blocks in the middle are operations linear plus nonlinear component. So this is the ReLU rectified linear unit that you see on the softmax. We have, it's a supervised method, so we use as an input some configurations that we characterize as order and as disorder, and we optimize the parameters of the filter so that we get statistically the correct answer on the configurations that we show. This was used by Melko and Karaskilla in this work that appeared on Nature by now 7 years ago. And what they show is that using a shallow neural network, so a network with just one hidden layer in between the input layer and the output layer, they were able to predict the critical temperature on the triangular lattice, having shown just configurations of the square lattice. Well, we had as an objective interpretability. So what we did was to use the support vector machine, which is a method that actually gives a decision function. The decision function acts as a boundary, and the decision function can be taken as an order parameter. So in this work of 2018 with Cinzia Giannetti and Davide Valacchino, what we did was to study the susceptibility of the decision function, which again is a derived quantity after training, and to compare it with the magnetic susceptibility. And you will see that the behavior is pretty much the same. And we extract the critical exponent of the correlation length and the critical temperature with an accuracy that is only marginally worse than the accuracy that you will do starting from first principle. So on the left, you will see, in fact, a traditional Monte Carlo analysis of the data in which I study the shift of the critical temperature as a function of the lattice size, and this determines nu and determines the critical temperature. On the right, I do the same, but instead of using the magnetic susceptibility, I will use the susceptibility of the learned decision function. And you will see, you can compare, and you will see that the results are correct. And the reason why you see an accuracy on the right that is a factor of 3, perhaps worse, of what you see on the left, is that in Monte Carlo methods, we can use techniques such as reweighting, because we know that observables are determined from a Boltzmann distribution. And with those techniques, we can improve the accuracy of the simulations, extracting the density of states. This was not available at that time on the right. And we do the same for the peak of these two susceptibilities. Again, similar results with marginally worse statistics on the right. This was the first extraction of critical exponents using machine learning methods. This is a summary slide that you will see here. On the left, well, on the top, I compare the standard Monte Carlo extractions, and at the bottom, I compare the machine learning extraction. You will see that the critical temperature is only worse by a factor of 2. A little bit of accuracy instead is lost by a factor of 3 on the critical exponent in the case of mu, and by a similar factor again on the critical exponent ratio gamma over mu. What I'm not discussing here, and I will refer to the paper that you will see at the top, is actually the symmetry of the system is not encoded in our approach, is learned. So this is a demonstration that the machine learning method is able to work out the symmetry. Let me now discuss reweighting, which I advocated as a tool to increase the precision, what you will see in this slide is single histogram reweighting. And what I'm using is a trick by expressing an observable which is taken over an ensemble generated with a coupling beta. I multiply and divide by the Boltzmann factor at another at a beta prime, at another inverse coupling beta prime, and you will see that I can map the two observables, so the observable on the left on the distribution generated at beta prime is mapped in the ratio on the right of the two observables in the distribution generated at beta. So this can be used to generate new data or to put together data when you don't have the simulations. Well, essentially moved by this observation, what we did was to see if the machine learning derived observables are legitimate observables of an ensemble system. So here we define the probability of classifying configurations in a given phase, and we measure that with the machine learning, with a Monte Carlo and with the machine learning result. And what you will see here in the black diamond is the point that we determined via a direct Monte Carlo, and the open diamonds are points that we measure again via Monte Carlo. The continuous line is the reweighted curve using only the information of the black point. So since this is a machine learning obtained observable, this is a numerical evidence that this observable actually satisfies Boltzmann statistics. On the right, you will see that this probability of classification in a phase can be used also to define the critical temperature by intersection of curves as a function of the lattice size. Another question that we asked is whether you can train a model on a system and then extract the physics on other systems. So what we did in this study is we trained the convolutional neural network that you will see on the IC model, and we used it to get a first determination of the phase transition for the POTS model at different number of states, where the transition goes from second order to first order as you increase Q, and also on continuous variables. And you will see that the determination is pretty much accurate. This can be used instead of training, so this reduces the problem of training. You can train a neural network on a system to get a first understanding of order-disorder phase transition. And once you have this first understanding, you can retrain on the system of interest. And if you unbox the neural network and if you see which variables actually count in the structure, you will see that pretty much in the language of neural network, the neurons that are activated are the same with all those systems. So when I have a bar, these are the links that count in the propagation to the network. So if I am in the disorder phase, the same links are actually activated. And if I am in the ordered phase, the same links are activated through all these systems. What this seems to indicate is that for the machine learning system, order-disorder phase transitions are actually more universal than they are from the physics point of view. We used this approach to determine the phase transition on the 5 to the 4 model. So we took the data, we reweight in mass parameters, and we identified regions where the phases are clearly separated. Then we retrained the networks in this region from these two values of the mass, and we repeated the scaling as in the Ising model. And these are the quantities that we extract, which compare favorably with the extractions that was performed in 2009 by Sheikh and Lomas. So now, are there any questions before I go on?
Yeah, I have a question.
Yeah.
So you've showed very convincing evidence that this idea can pick out order disorder phase transitions, at least in these examples, or probably more generally. Do you think that it might be possible to also find disorder phase transitions? Like, for example, if you could have a phase transition between two different SPT phases.
Yeah,
everything looks disordered, but there's a phase.
I think it is possible, and this is actually was one of the motivations, together with the phase transitions that do not admit an order parameter, like topological phase transitions.
Exactly, that's the thing.
But I'm not there yet.
Okay, fair enough. And it
so,
also
I mean, you know, that was the motivation. So that was the motivation of testing all this machinery on non-phase transitions, because if it doesn't work there, there's no point.
Of course, it makes complete sense. Yeah.
But I mean, the results are very promising, and we believe that we can go in that direction.
Great. And Andrea seems to have a question. So,
yeah, hi Biagio.
Andreas.
I have a question regarding the previous slide. I mean, the one before. I mean, where you used so let me understand. I mean, you extracted the weights for the Ising model, and then you use the same weights to extract the phase transition in the pods?
Well, this is what has been done here.
Okay.
In fact, what you see here, these are trained independently on the models, and we wanted to know why actually this approach of using a network trained on the Ising model was working on the pods and was working on the 5 to the 4. And this is the explanation. If you train directly on the model, the ways that you would expect to be activated are actually active.
Okay. So one more question, which is a more technical question. I mean, so in the previous slide, so the number of I mean, there is a difference between the amount of data between the Ising model and the PODS model, for instance. I mean, how do you take care of that? I mean, or you just
well, it's just I mean, it is just a variable that you put. And so there is a difference in phase space in the sense that you get more variables. But if you fix the lattice size, the same number of variables appear there.
So you need to have the same number of variables at the end of the day.
Yeah.
Okay.
The same number of lattice points, that will do.
Okay.
And instead of putting a Z2, you may put 3 states, 4 states, 5 states. And that works equally well.
Okay, fine. Okay, thanks.
Thank you. Okay, so now what I'm going to describe now is whether we can define an order parameter unboxing the decision function or the classification function of the neural network. So essentially, there is the final layer. If we go, for instance, here, the softmax layer decides through a function that smoothly goes between 0 and 1 or between -1 and 1, whether you are in one phase or the other. So this is your classification function. And the classification function, as we were saying before, could be for the support vector machine, can be interpreted as an in-order parameter. So what we want to do now is to take this function, which goes between 0 and 1, and use it as an observable by coupling it to the Hamiltonian through a coupling y, and multiplying by the volume because it's a scalar observable. So now I'm extending, sorry, let me go back. I'm extending my system with these additional degrees of freedom. Now I can compute, for instance, the expectation function of this function using the standard thermodynamic approach, for instance, by taking the partial derivative of the log of the partition function with respect to the coupling y. This is what happens. So what you will see in the middle is, now I'm back on the Ising model. So what you will see in the middle, this is the standard Ising model. So the coupling y is equal to 0 in the middle. And as you vary y, you will see that the decision function actually, as you go to negative y, the decision function will go towards 0. And as you go to positive y, the decision function will go towards 1, which means that this is actually changing the phase of the system pretty much as you would expect from an external field. And you will see the susceptibility of this function, which will peak at some point when we have the phase transition. So by varying beta, I can induce a phase transition with this function y. Now, if the interpretation is correct, this y has to be related to the magnetization of the Ising model. So it has to scale with the critical exponent of the Ising model, which is what we have done by using renormalization group methods. And what you will see is that this order parameter will give us access to the critical exponent, to magnetic critical exponent, through this theta, which again compares favorably with the expected value. So again, I'm augmenting the information that I can extract from my configuration by introducing a parameter which was not there before, and by reweighting in configuration space using a coupling in that direction. I'm now going to the last part of the seminar, which possibly has been a little bit quicker than I expected, but this will take a while. So what we have done in, as the last step so far in this program was to use renormalization group methods to to use machine learning methods actually to invert the renormalization group. So what we want to do is to use this method to generate configurations on larger lattices, starting from smaller configurations and near criticality with negligible computational cost. This makes sense for systems, for instance, in which you are interested in the phase transition. So this is not a new idea to go from small configurations to large configuration. It was already explored by Swansea in 1979, and it was formalized by Ron and Brandt, and then Ron, Brandt, and Swansea proposed a calculation based on standard Monte Carlo in 2002. And the method does work if you have enough information to compute the renormalized Hamiltonian of the system. And machine learning offers an approach that is different from the traditional first principle one. And again, this has been done by Esfimio, Beach, and Melko, by Li and Wang, and by Shina, Mori, Tomita, Lee, and Okabe. in spin systems. In our work, we have given the first implementation for a quantum field theory. Now, let me start with a little movie that will not surprise any of you. Again, I will start from the Ising model, and I will start from a lattice which is 768 in size because I need to block. And as a block, let's see what happens. So I'm starting from 3 temperature. One simulation was taken at T equal Tc. Another one was 3 per mil above Tc. And another one was 3 per mil below Tc. So if I'm starting below Tc and I start to block, the renormalization group flow will naturally lead you to smaller temperatures, so you will see a magnetization that emerges as the system is driven from the unstable fixed point. Analogously, if I start from about Tc, you will see disorder emerging, and again, you will flow to a temperature that goes to infinity. If I'm starting at the critical point, well, you know that there is scale invariance. If I keep shrinking, increasing, and zooming, then I will not see any obvious difference with the system I've started from. Yeah. So this is the standard renormalization group that we show in lecture theaters. Now, let me see what happens instead with the inverse renormalization group. So with the inverse renormalization group, if I start from the critical temperature again, as I enlarge my lattice size, I should see still the same feature of the system. At higher temperature, if I start from a disordered phase, I should see criticality emerging as I keep extending my lattice size. And if I start from a completely ordered phase, again, I will flow towards the critical point. So I'm actually reversing the renormalization group flow. Now, I love you to tell you that this was actually the result of a simulation, but in fact, what it is, and what most of you would have certainly realized, is just the previous movie played backward. So now, let's see if we can actually we can transform these ideal settings in some practice. So, what I'm trying to do is I will generate lattices at some size L0, and I will scale them up by a factor B, 2 by convention, until I reach a size that is a power of 2 larger. So why do we want to do that? Well, if I use, for instance, one motivation other than studying precisely the renormalization group properties and the critical exponents, one motivation is, from a computational point of view, the fact that the correlation time for generating configuration grows exponentially with the correlation length, which means that, strictly speaking, if I am in a second-order phase transition, it is impossible to simulate at the critical point, and simulations will become slower and slower as I approach the critical point. Now, we all know that the renormalization group is, in fact, a semigroup, and what it means is that I can block easily through a recipe, but I will not be able to unblock because this is an ill-defined operation. For instance, we will see here some examples on the Ising model. All these blocks gives you +1, either by the majority rule or by the flip of a coin. Assume that you have flipped a coin when you get an equal number of spin and you get +1. So now, if I'm trying to zoom in something which a certain scale appears to be a +1, I will not know which ones of these blocks or others I mean. Of course, I can exclude some blocks, but I cannot choose. If I have a scalar field, so a continuous degree of freedom, the situation is even worse. Because, for instance, if I'm averaging the block on the left, I'm getting the same number, which is open 4, than if I'm averaging the block on the right. Okay.
So, sorry, I'm a little confused about the
Sure.
the blocks for easing spins.
Yeah, please.
What I think the last two look identical, right?
Yes, the light 2, yes, that was my mistake, actually. I wanted to put
But
-1. Yes.
Are you using majority rule or just +1 in some blocks?
I'm using majority rule here.
But here there are equal numbers.
Yeah, equal number. I suppose that I flip the coin and
Oh, you flip the coin. Yeah. Okay.
So, I mean, with Ising model, there is still a finite number of blocks that will give you a given spin value. If you have a continuous degrees of freedom, actually there is an infinite number of blocks. So what do? Well, we start from a set of configuration generated from Monte Carlo at size L. Now, we using a machine learning algorithm, what we like to do is to derive a set of configuration derived at a lattice L prime, which is BL. Say 2L, so I'm redoubling the lattice size. I'm assuming, and this is where actually the assumption is important, that the ensemble derived at L prime is distributed according to the Boltzmann distribution of the original smaller lattice as size L. So this will enable me to compute without having to map flow of coupling observables on the lattice L prime. And then by using crossing of curves, I can compute the critical quantities, which essentially amounts to using a Monte Carlo renormalization group. So the advantage is that all the numerical effort is done on small lattices, if I'm able, of course, to implement this program, of which I've not given you any indication whatsoever so far. And as the effort is relatively cheap. But critical to the process, as Igor was implying, is the blocking method I'm choosing, but also the Monte Carlo, the machine learning algorithm, and the assumption of the Boltzmann distribution that I have just illustrated. Now, what is the equivalent of the majority rule when I have a continuous variable? Well, what I can do is I can decompose my block in the positive part and the negative part. And what I can do is I can block the phi by using the positive part if the positive is bigger than the negative, or the negative part otherwise. So this is a possible generalization of the majority rule in the Ising model, which is better than averaging. And in order to build the machine learning blocking of the lattice, so what I do is I first go in the direct way, and then I optimize the machine learning method so that it reconstructs on average the configuration from which I've started. Well, essentially blocking downwards, it's easy. Blocking upwards is the transpose of the filters that I've used to block, to reduce the lattice size. So this is what we have if I start with a lattice, which is an 8 squared, and I block all the way to L equals 64. So I'm training only from L to 2L. And once I have the filter, which extend my lattice configuration, I just use it. So I don't need to find, for instance, from L to 2L, and then from 2L to 4L, I need to retrain, and then from 4L to 8L, I need to retrain. It's just a matter of optimizing the filters, and I can use the smallest lattice and augment all the way to any size of my liking. And you will see some examples, again, on the file to the fore. The curves on the red ones are generated directly, and the yellow one, the broken ones, are instead obtained by applying the transformation. And you will see that since the direct curve are steeper, the yellow curves are closer to the critical point. You can see how close that they are. You can basically map the flow of the coupling by intersecting these lines horizontally. Where the lines cross, this is the critical value. And again, if you remember the values that I've shown at the beginning, this is where it's supposed to be. Now, we can determine the critical quantities by rescaling the relationships for the magnetization. For instance, if I'm starting from two different magnetization, they goes in this way with the reduced temperature, and with the two corresponding correlation length, they scale with the minus beta over new exponent. So by taking the log of the ratio, I can get B over nu. And in fact, since in the limit for the magnetization going to 0, this is undetermined, I will need to use L'Hopital rule, and I will need to compute derivatives. Now the denominator is trivial because I have the relationship from the lattices, and the numerator, I just get it numerically. And similarly for the other ratio of critical exponents.
Quick question. So I'm a bit confused about the logic. I mean, if I understand correctly, you just have a specific mapping from small lattices to large lattices without adding any extra information. And the only difference is that on the large lattice, you would use different observables than the ones you would compute on the smaller lattices. But then isn't it just easier to take the observables from the large lattices and just map them and use them on the small lattices instead of mapping the whole configuration to the large lattice?
Well, I'm not sure I understand the question. So I can only...
at the end of the day, you're not adding any information, right? Any observable you compute on the large lattice, you could equally well compute it on the small lattice. It will just be some complicated observable, right? But is it still to compute it?
In a way, it's what we do, because we don't know where the coupling is actually mapped. So what you do is you take the configuration, okay? So you take the configuration and you weight with the Boltzmann factor of the smallest lattice. So you compute the observable and the weight, which was what I was trying to say a few slides back. The weight is the Boltzmann factor of the smallest lattice. But the observable is computed on the largest configuration. Okay. So the averaging is taken using the weight of the smallest lattice. Yeah. So in a way, it's a mix of the two, if you wish, or it's what you are saying, if I interpret correctly the language. Okay.
Yeah. Okay, thanks.
Okay. So, and this is what we find for the exponents. So here is the, when I take this ratio, of course, I have one starting point, so I need to take two values. So this, as a function of the pairs of the lattice sizes, these are how the ratios of the critical exponents are approached. The horizontal lines are the critical exponents of the Ising model. We know that lambda phi to the 4 is in the equivalence class of the Ising model, in the universality class of the Ising model. The configurations here have all been generated for the lattice size equal 32, and they have successively augmented all the way to 512. And we have taken all the pairs going towards 512. And you will see that as you enlarge the system, you approach the values that you would expect analytically. Right, so with 10 minutes to spare, I believe I'm at the end of the presentation. So what I hope I have demonstrated is that machine learning can offer a novel angle to look at phase transitions. Of course, let me say something straight. There is no advantage at using machine learning when you know already the answer from first principle, because machine learning at most will give you a more inefficient and statistically accurate or inaccurate, depending on the problem, answer that will reproduce what you already know. However, if you don't know the answer, or if you pretend you don't know the answer, then you can show that machine learning enables precise calculations of critical properties with no assumed knowledge of the underlying symmetry. For instance, and we go back to the disordered system, which is what I like to try as the next step. Then machine learning can be used to discover observables, which can be order parameters, can be phase indicators, when you have no other way, or you don't know of a smart way to construct them using first principle. The inverse renormalization group, through which you determine the most likely starting configuration that will produce you a smaller blocked lattice using an optimization through a set of filters, is another demonstration of the potential of machine learning. The current focus is on the interpretability. Of course, other people in the field are using machine learning for other reasons. We also have a parallel line of work. Here, I've shown you machine learning for statistical systems and quantum field theories. In other works that is still ongoing, we are showing that actually you can use quantum field theories to build machine learning methods that are more expressive of those that are currently available in computer science. And thank you very much for your attention, and I'll stop sharing.
Thank you, Biagio. That was great. Are there any questions from anybody? Maybe I can get things started. So I had a question on the next to last slide, which you don't need to show. So you were saying that with this inverse renormalization group, you can get the critical exponents with either no critical slowing down or negligible critical slowing down.
Yeah.
For things like the Ising model, there are other ways of doing that. For example, using worm algorithms.
Yes.
I mean, I don't know if there's a good question at this stage in the program, but how do these two methods compare in their numerical efficiency? Because that's
well, there is, I mean, the critical slowing down actually is something that when you have a Monte Carlo algorithm, you cannot avoid. You can reduce it, but it's related to the physics of second order phase transitions. In fact, with machine learning, we completely avoid it using the fact that we simulate on small lattice. So the critical slowing down is determined by the lattice size at which we simulate. All the others are determined through augmentation.
I see. So indeed, I mean, worm algorithms significantly reduce the amount of critical slowing down. They don't completely eliminate it.
Yeah, they're not, yes.
Your approach, it is completely eliminated.
It is, well, you know, it has the critical slowing down of the smallest lattice that of the lattice that I decide to simulate.
I see. But then the question kind of remains, doesn't it? I mean, how does it compare in the efficiency of actually doing this? I don't know if you've looked into it.
Yeah, it could be system dependent, but I mean, asymptotically, assuming that there is no hidden surprise anywhere, and that makes our augmentation fail, I don't know, lattice 3000, 4000, 4 million, who knows. I mean, assuming that this does not happen, asymptotically, our method is completely free from critical slowing down. So asymptotically, you will always reach an exponential time with warm algorithms or similar.
That's right. I see. Thank you very much. I think Marco had his hand up next, and then Ofer. So Marco, please go ahead.
Yeah, thanks for a nice talk. My question is a bit related to these possibilities that you were mentioning in the conclusions. In particular, I was wondering, I mean, what is your take or your opinion on applying machine learning techniques to problems that are considered to be computationally very hard, like, for example, trying to tackle systems that have a severe sign problem. And even if in that case, one can expect to see, for example, some effects like the silver blaze problem already seems something slightly non-trivial to me that could be studied, for example, in this type of approach. I was wondering what's your opinion on this. Thanks.
Yeah, no, thank you. You know, when I started this about 5 years ago, maybe even more, I had this prejudice that machine learning could actually solve all the problems without any input. The more I look into it, and the more, I mean, you know, the human in the loop, the physicist in the loop is very, very important. So I think that machine learning has a lot to say as an additional tool in the toolbox. I don't think that machine learning can be the main tool or well, certainly not the only tool. Maybe it can become the main tool in the toolbox of a physicist at some point in the future. But I think that the physicist and the physical intuition is still very, very important. For these very hard same problems that you mentioned, I don't think that we have the intuition yet to use machine learning in an effective way.
Okay, thanks.
Thank you.
So one of the good things about traditional lattice simulations is that we know how to estimate the errors very well, both systematic and statistical. I mean, so how do you estimate the errors for these machine learning methods?
Well, it depends. So there are two sources of errors. One is still statistics, and the other one comes, for instance, from the training, which, again, you can trade the systematics with the statistics using methods which essentially amount to the bootstrap. So you redo the same process on a different training set, and if you have cycled enough among all your training sets, then you get a reasonable estimate of the error. So your final error is your Monte Carlo error, depending on the method of machine learning that you use, plus your training error that you have that you can still estimate.
But these are just statistical errors. I mean, but what about the errors like in the systematics of this inverse renormalization group process or things like that? How do you estimate those?
Well, there could be some systematic errors that I'm not aware of. There are certainly systematic errors. One systematic error is that I'm using the Hamiltonian, the original Hamiltonian. We know very well that I should be adding couplings that I'm happily neglecting and hope for the best. And fortunately, we go for the best in this case. Otherwise, I will need to estimate additional couplings, etc. These sort of errors remain, any truncation error related like that, no, I'm not able to estimate it yet. Okay. This is also what happens, for instance, I mean, you know, much as I like the lattice and I've built a career on the lattice, I mean, not all the lattice methods are free from this type of approximations. So, I mean, you know, essentially there are errors that you can estimate because in machine learning, there are the same sort of problems, and people call them bugging and boosting. But these are methods that we also use in lattice field theories and in statistics, calling them in a different way. And then there are uncontrolled approximations that we do not estimate. what I've shown you, for instance, if you forget for a second about the inverse renormalization group we just distruncated Hamiltonian, if you go back to the analysis of the phase transition, there is the choice of the architecture. Okay, so this is the main source of systematic error. There has been a paper recently by D'Alessandro Tantalo and a student on this collaboration, which essentially what they suggest is to do again a bootstrap over a set of architectures. Okay, so this can be handled. I mean, you cannot quantify, you can certainly estimate, you can get an order of magnitude, assuming that again what you have is representative. Thank you.
I have another question. So in the beginning, you explained that you were going to follow like a supervised learning approach where you tell your neural network some examples of ordered and disordered phases. Is it conceivable to use the unsupervised approach where you don't put that in at the beginning with the goal of eventually studying phase transitions that are hard, that we don't have great ways?
It is conceivable, and there have been works in this direction. For instance, Andreas has a beautiful paper on Ising model using autoencoder in a full unsupervised way. It is conceivable. I'm slightly biased toward the supervised approach for what I've said when I've answered Marco's question. I think that, the more information you know, the more information you put in, and the more you get out with.
Right. No, of course that makes sense. Yeah. No, the reason that I'm asking is with the motivation of, if it's not easy to give examples of what the two phases look like, because a priori you might not know whether there's a phase transition or not. So what example do you give?
But that's what you say.
Huh?
What you say is actually interesting because you don't need a phase transition, in fact, to do classification, and we have tried that. So you can get two states in two betas, say, both in the same phases, and you can build a parameter that will tell you whether you are closer to one of the two, even if they are on the same phase.
I see. That's interesting.
This can be done.
That's interesting. I see. Very, very interesting. Okay. Any other questions?